Okay, we're going to go through some examples of trig identities that you saw in the lesson. So a trig identity is an equation that is true for all values of the variable. And to prove that an equation is an identity, you're going to show that the left side and right side of the equation are equal. And sometimes you may need to factor or find a common denominator. So some helpful steps to help you solve or prove trig identities is to try to write the given expressions in terms of sine and cosine as much as you possibly can. You might need to use compound angle formulas to rewrite all ratios in terms of a single angle. So you might need to rewrite it in terms of just sine of theta as opposed to sine of 2 theta. You might also want to begin with the more complicated side and try to simplify it. And don't give up. You should expect to make mistakes. Each trig identity has a small trick. The more you practice, the more tricks you will know. Okay? So all the trig identities that you should know for now for the grade 12 course is the Pythagorean identity, the quotient identity, the reciprocal identities. Those are the three that you learned last year. And then the cofunction identity, the compound angle identities, and then the double angle identities. And really, if you know the cosine and sine compound angle formulas, then you should be able to derive the tangent one and the double angle ones as well. Okay. So I'm going to go through some of the examples from the lesson. So the first example I'm looking at is question 1e, where it says prove the identity. And so you're going to write it as your left side and your right side separate. And your goal is to try to make the left side and the right side look exactly the same. And once you do that, you have proven the identity. Okay? So I'm going to look at the left side. You'll notice that on the left-hand side, I have a fraction. On the right-hand side, I do not have a fraction. On the left-hand side, I have cosines and sines. On the right-hand side, I have a tangent. Okay, so ideally what you want to try to do is try to make the two sides look exactly the same, which means they should have the same kind of trig ratios as well. Okay, so if you only have cosines in one, then you want to have cosines on the other side as well. Okay, so on the right-hand side, what I'll do to start is rewrite this so that I no longer have a tangent. So I would rewrite this using the quotient identity. And so I get 1 minus sine x over cos x. And I can see that here I have two terms, whereas on the left-hand side I have one big fraction. So maybe I can get a common denominator here and multiply the numerator and denominator of the 1 by cos x. Okay, so if I multiply numerator and denominator by cos x, what I end up with is cos x minus sine x all over cos x. So now it's starting to look a little bit more like what I have on the left-hand side. So now I'll work on the left-hand side a little until the two sides look exactly the same. So on the left-hand side, what you'll notice is I can actually factor the numerator and I can actually factor the denominator. So let's see what happens if I just factor the denominator to start. So if I factor out what's common in the denominator, which is cos x, what you'll notice is what I remain with is cos x plus sine x. And if you look at the denominator on the right-hand side, I can see where that cos x might match up. Okay? So somehow this cos x plus sine x has to disappear. It has to be canceled out. So if I look at the numerator now, you'll notice that it's actually a difference of squares. And so I can factor this as a difference of squares. And you'll notice that there's a common factor in the numerator and denominator. There's a factor of cos x plus sine x in the numerator and a factor of cos x plus sine x in the denominator, which means I can cancel those out. And all I'm left with now is the exact same thing on the left-hand side and on the right-hand side. So that means we have proven the identity. Okay? So that's an example where you're factoring and using some of the identities that you know from last year. This idea I'm going to prove is a bit of a messier one, so I'm writing this on a separate sheet of paper. And so again, I'm trying to make the left side and the right side exactly the same. And you'll notice that here I have some compound angle formulas that I can use to help make this in terms of a single angle. So you'll notice that this one here is in terms of two angles, same thing here. Whereas all the questions, all the parts that I have on the right-hand side, or all the terms that I have on the right-hand side are in terms of one angle. So just an x or just a y. So I'm going to start with the left-hand side. And I'm going to use my compound angle formulas to rewrite this part. So I would have cos x, cos y, minus sine x, sine y for the first part. So cos of x plus y is equivalent to this. And then cos of x minus y is equal to cos x cos y plus sine x sine y. Okay, so now it's not really looking like the right-hand side yet. So instead what I'm going to do is I'm going to actually expand and use the distributive property to distribute the binomial times the binomial. And so if I actually do the distributive property, I have cos x times cos y multiplied with cos x and cos y again. So that means I'm multiplying cos x by itself twice, so that'll give me cos squared x. And I'm multiplying cos y by itself twice, so that'll give me cos squared y. So far that's just the first term times the first term. So I'm going to continue to multiply the first term here with the last term there. So just using the distributive property. And I get sine x sine y and cos x cos y. And I'm going to continue now the second term with everything in the other brackets. So minus sine x sine y and cos x cos y. And then this times the last one, which will give me minus sine squared x times sine squared y. Okay, so now that big mess, so in case you were wondering how I got this is sine x times sine x and sine y times sine y. So that gives me sine squared x sine squared y. Okay, and so now I can simplify this. You'll notice that these two middle terms are exactly the same, so I can cancel them out. And so all I'm left with now is cos squared x cos squared y minus sine squared x sine squared y. Okay, it's starting to look a little bit better. It's in terms of only one angle now, just like we had on the right-hand side. But you'll notice on the left-hand side, I have some sine squared terms, but on the right-hand side, I have no sine terms at all. So I'm going to try to get rid of those sine squared terms. You'll also notice that on the right-hand side, I have a 1, okay? And on the left-hand side, I don't have any number terms, so I'm going to try to figure out how that came about. Okay, so let's start with the sine squared x and the sine squared y. Now, the only way that I know how to get rid of sine squared x is using the Pythagorean identity. And so if you think back to the Pythagorean identity, we know that sine squared x plus cos squared x equals 1. And so if I rearrange this to isolate sine squared x, I would get 1 minus cos squared x. And so that's what I'm going to do. I'm going to replace the sine squared x with 1 minus cos squared x. Because my goal here is to try to get it only in terms of cos and not in terms of sine. And then same thing here, I'm going to replace the sine squared y with 1 minus cos squared y. And again, now I have a bunch of multiplication. So again, I'm going to expand and simplify. And you'll notice that it's starting to look more like what we had here. We needed some cos squared x and cos squared y terms combined through addition. Whereas here we only have it combined through multiplication. So let's expand and simplify that part. And so if I expand this, I get 1 minus cos squared y minus cos squared x plus cos squared x cos squared y. And if I simplify this even further, there's no like terms here, so I'm going to expand that negative that's at the front. So I have cos squared x cos squared y minus 1 plus cos squared y plus cos squared x minus cos squared x cos squared y. And you'll notice that this term and this term are exactly the same but opposite signs. And so now all I'm left with is cos squared y plus cos squared x. Oops, plus cos squared x. And then minus 1, which is exactly the same as the right-hand side that I have all the way up here. And so the left side is equal to the right side, and we've proven the identity. Okay, so that was a bit of a messy one. It had a lot of steps to actually get through it. So you had to use a Pythagorean identity, you had to use a distributive property, you had to use compound angle formulas, lots of mess, but eventually it looks like the right-hand side. Okay, so the last example I'm going to look at is how to prove trig identities using counterexamples. And so you're not actually proving an identity, you're proving that the identity is not true. And so counterexamples can be used to prove that an equation is not an identity. Okay, so you're basically proving the left side is not equal to right side. So since identities must be true for all values of the variable, to prove that an equation is not an identity, you need to find just one value of x such that the left side and the right side are not true. So in an identity, all values of x have to satisfy the equation. So as long as you find one value that doesn't satisfy the left side and the right side, then you've proven that it's not an identity. Okay, so remember to choose values of the variable that are easy to work with. especially the special angles. Okay, since you won't be using a calculator, special angles are the best option you can use. So we're going to look at one example from the lesson. And so the example says, use counterexamples to prove that the following equations are not identities. So I'm only looking at the first one here. And so you have sine of x plus y is equal to sine of x plus sine of y. So here what you have is x plus y in total represent the angle, whereas here you have sine of one angle plus sine of the other angle. And you want to prove that this is not an identity, so you want to prove that this is not equal to each other for some particular value of x. So I just chose a value of x and y, and so the value of x and y that I chose are pi over 4 and pi over 4. Those are relatively easy. You could have used pi over 3 or pi over 6 for either one of them, or you could use different ones too, so you could have used pi over 3 and pi over 6. It doesn't really matter. So I just used pi over 4 because I thought that was easiest. You could have also used pi, or you could have used 2 pi. Any of the angles that are easy to work with are the ones you want to choose when you're trying to prove a counterexample. So on the left-hand side, I have sine of x plus y. So I'm going to replace x and y with, pi over 4. And so I get sine of pi over 4 plus pi over 4. And so what this means is that I'm looking at sine of these two angles combined. So I can either use my double angle formula or my compound angle formula to do this, or what I could do is just add up the angles together, which in this case would just be pi over 2. And so the sine of pi over 2, if I'm looking at my angles, this would actually be positive 1. Okay, so what that means is the left side is equal to positive 1. On the right hand side, if I do the same thing, I'm looking at sine of pi over 4 plus the sine of pi over 4. And using my special angles, sine of pi over 4 is 1 over root 2 plus 1 over root 2. And so 1 over root 2 plus 1 over root 2 gives me 2 over root 2. And so since the left side is not equal to the right side, therefore sine of x plus y equal to sine x plus sine y is not an identity. Okay? So it might be true for some values of x and y, but it's not true for all values of x and y, so that means it is not an identity.